Produced by PI Media. Blockchain.
If men were angels, no government would be necessary. If angels were to govern men, neither external nor internal controls on government would be necessary. In framing a government, which is to be administered by men over men, the great difficulty lies in this. You must first enable the government to control the governed, and in the next place, oblige it to control itself. When James Madison wrote the 10th Federalist paper, his colleagues were in the throes of developing a radically new type of country, one which broke with thousands of years of human history by rejecting the notion that one entity, the King's Palace, should have control over every aspect of a nation. Instead, the United States of America would be a representative democracy, one which decentralized the locus of power by giving every citizen equal voting right to help guide the outcome of their shared environment. Do you see where I'm going with this? Decentralized consensus sounds complicated, and in a sense it is, but it's not a totally unique problem in human history. In fact, in your own life, you've probably faced situations where similar problems have cropped up. Perhaps it happened during a group project, or a team sports event, or a time when you and your friends had to decide who deserved the last slice of pizza. In such scenarios, different parties have opposing interests, but no single party necessarily has more power than the other, so a method must be agreed upon in order to reach a fair solution to some conflict. Of course, reaching consensus isn't always so clear-cut. Even when the object of a conflict is just one slice of pizza, there are any number of ways to achieve resolution. The group can decide that whomever has the fewest slices thus far deserves the last. But what about when there's a tie? You could say that the hungriest person deserves the slice, but that means you'll have to rely on subjective evaluation, easily rigged by a greedy group member. Maybe you could split that last slice. Whatever you decide, problems arise if not everyone is okay with how things end up. In this episode of the Orbs podcast, I'll explain what consensus means in a blockchain context, how today's most effective models are designed, and why, even after a whole decade, this problem is still hotly debated and far from solved. Along the way, you'll be hearing briefly from two individuals with the credentials necessary to understand the ins and outs of just such matters.
Hi, my name is David Yakira, and I work for Orbs Research team. Helped develop the Orbs consensus protocol, Helix.
Hey, I'm Steven Goldfeder. I'm a PhD candidate at Princeton University, and I do most of my work in cryptocurrencies and cryptography relating to cryptocurrencies.
And so, we begin. Consensus is designed to solve the problem of agreement in a decentralized system. In a centralized system, there are no different parties and thus no conflict in reaching an agreement. In a decentralized system, there is no central bank, no store owner or credit card issuer keeping a record of your purchase with whom you can trust that a transaction has been enacted according to plan. Instead, all parties involved must have some means of coming to agreement on any new instance of an interaction in the system. Of course, if everybody plays nicely, a majority vote on the integrity of a blockchain ledger is a straightforward consensus that is decentralized, permissionless, and open. But when it comes to money and power, we can expect that not everybody will play nice. In Bitcoin's ecosystem, for instance, Every participant is anonymous, so there's no guarantee that one person or group can't stack the chips in their favor. Therefore, in order for the system to hold together, it requires a protocol for dictating which transactions are verified and which are invalid, in, say, the case when someone tries to steal from someone else. I spoke briefly about what this solution is in a previous episode of the podcast. Now, let's dive a little deeper. Satoshi Nakamoto, inventor of Bitcoin and therefore blockchain, chose a consensus solution called proof of work for his network. Proof of work actually predates Bitcoin by quite a bit. It was invented by two computer scientists, Cynthia Dwork and Moni Noer, with the intention of providing a solution against spam mailers. The premise, in short, was that mass spam mailing was only profitable for its ease of access. Since emailing requires so little effort, a spammer could theoretically send out 10,000 separate emails, and even a 0.1 response rate would be well worth their time. That's 10 new customers just about for free after all. However, if spending a large number of emails required even a moderate amount of computing expense to accomplish, then sending out that many emails would no longer be worthwhile. Bitcoin's proof of work system does something similar in the realm of monetary transactions. Anytime one party transfers any amount of Bitcoin to another party, a third party, called a Bitcoin miner, will have to conduct some amount of work in order for the transaction to be approved. In order to do so, the third party dedicates significant computing horsepower to solve what amounts to a mathematical puzzle, one which, like the game of Sudoku, requires time and significant resource to solve, and little more than a quick check to verify. In return for their expense, and for being the first to finish the proof, the miner is rewarded with some more Bitcoin of their own. The math functions themselves aren't straightforward at all. In addition to being quite complex, they involve randomness. As a result, many different miners might try to solve the same math problem, and whomever has the most computing power at their disposal will have more of a chance of completing the problem first. Because it's hard to wrap one's head around complex computational mathematics, you can think of the process of Bitcoin mining kind of like this. We're playing a game. It's you and two friends. The prize is $5. I begin by handing you a pair of dice. I hand one of your friends 2 pairs of dice, and the other 3 pairs. When I say go, the first person to roll 2 sixes wins. What can we say about this game? Well, everyone has a shot at the prize, because any given roll of a die will come up with a random outcome. However, not everyone's chances of winning are equal. Assuming no wrist injuries, of course, those with more die will have a greater chance at coming up with at least 2 sixes in one roll. That, in an oversimplified sense, is what's going on in proof of work. Bitcoin mining requires much more time and effort than rolling sixes, but each miner has a shot at the transaction earnings in proportion with what the power of their computer rigs allows for in running through the numbers. More importantly, Bitcoin is designed such that scammers are organically dissuaded from attempting to push through invalid transactions. Here's Steven Goldfeder to briefly explain how that works.
Miners are rewarded for finding blocks, but in particular, miners are rewarded for finding valid blocks. And if a miner submits an invalid block, they're not going to get that reward, and their block and all the work that they expended to find a valid block will be wasted. So this incentive system that is enforced by the consensus incentivizes miner not to include bad transactions in their block, because if they do, others in the system will find those errors and will say, hey, your block is invalid. Now, the amount of work that it takes to find a valid block is very, very high. The amount of work that it takes to validate the Bitcoin transactions in a block is pretty small. So it's worthwhile for miners to do the little bit of work to check that they're only including valid transactions in their block, because what they would not want to do is to do all the work to find a valid block and then find that they have an invalid transaction in there.
As one example, let's say a malicious actor has 1 Bitcoin which they try to spend twice. Once on a used car, another time on a diamond necklace. This is what's called a double spend, where two overlapping transaction requests are sent for processing. If one of the vendors receives their payment first, the other will not. But what if both transactions get confirmed at the same time? Now we have two versions of the blockchain. One where the Bitcoin was sent to the car salesman, and another where that same Bitcoin was sent to the jeweler. Now there's a race. Whichever line can receive the next block in the blockchain will be considered the winner, and the losing blockchain will have seen its transactions invalidated. But double spends are just one way that scammers might try to rig the Bitcoin system in their favor. There's also 51% attacks. The idea that if one agent were to control over half a blockchain's computing power, it would essentially have full control over the whole system. We can be safe with the knowledge that in any large-scale platform like Bitcoin, attempting to own the same amount of resource as the entire rest of the network combined is a practical impossibility. So proof of work is a quite elegant model, not too complicated, naturally secure, and it has fostered an enthusiastic community of Bitcoin miners. Now, allow me to turn the tables. There are real problems with proof of work that are holding Bitcoin back from even greater success. For one thing, the effort required for new transactions to be added to the blockchain means significant latency periods. I spoke at length about that issue in our episode about scaling. Really though, in any discussion of proof of work, there's one big elephant in the room. I mentioned it briefly in our episode about the history of blockchain. I'll let David Yakira kick us off.
The process cost of every transaction in a proof of work based blockchain is very expensive. Right? If you compare this to other platforms that let you run code like AWS, then the cost is, I don't know, times what factor? Probably a very high factor. And this is because of the access, proof of work that you have to do, which is much more expensive than just running the transaction.
Bitcoin miners, as of this writing, consume approximately 175 million kilowatt hours of electricity per day. For reference, the energy it takes to run Bitcoin equals the energy it takes to run the entire nation of Switzerland. To process even just one Bitcoin transaction requires enough electricity to power one American household for an entire month. Now that I've described to you how mining works, you can probably imagine why it's so resource intensive. Because more computing power means a higher likelihood of solving proof of work problems, and because only the first miner to solve a problem actually gets paid for it, miners are in a constant battle to build up. Some miners pool their resources together and then share their winnings, leading to more centralization of the network. Oftentimes, though, it's just about buying and running behemoth computer systems. When it comes down to it, really, Bitcoin miners are something less like mathematicians or even computer scientists than owners of mini transformer Autobots, monster machines that run through insane amounts of data in no time at all, and in doing so, consume electricity like nobody's business. To cover the costs of running those systems, miners often need to exchange their mining earnings for fiat currencies, which contributes further to the devaluing of the coin overall. But wait, I'm going to turn the tables around on you just one more time. Here we have this dichotomy, an elegant security system, but a high energy expenditure. When I went to speak with Steven Goldfeder, someone who lives on the cutting edge of research in exactly this field, I had some questions about the cost-benefit of proof of work. I asked him, can this really be considered a successful model if it requires so much to maintain? His answer was not quite what I'd expected.
Proof of work spends a lot of resources, but the question is this really wasting the resource? Well, not necessarily, because we're getting something very valuable. As an example of something to think about the cost of securing a regular currency. You go to your even to your local branch of the bank, you see security guards, you see vaults, and of course there are many security measures that happen behind the scenes. You also, when you're driving, sometimes you might see an armored vehicle moving cash from one place to another, and there are real security costs to securing a traditional currency as well. So, and it's clear that we don't look at the security guard in a bank and say, well, this is a waste. We say, well, this is something that's necessary to secure our banks and our financial system. So sure, proof of work does spend a lot of resources, but it's not clear that that's a waste when you're getting something quite valuable. That being said, of course, there's an open scientific question and there's open debate on whether we can do better than these existing proof of work schemes. I think the jury's still out about these systems and whether they can give us the same guarantees of proof of work. But if they do, then sure, it would be great to move over to them. But right now, what we know is proof of work is proven and it works. No pun intended.
Blockchain.
Perhaps only time will tell whether the benefits of the proof of work model are worth its cost. Regardless, as a result of Bitcoin's demonstrable issues of scale, other blockchain platforms have experimented with different consensus models. The most well-known alternative to proof of work was first proposed in a Bitcoin forum blog post. User Quantum Mechanic. Title: Proof of Stake instead of Proof of Work. July 11th, 2011, 4:12 a.m. The post began.
I'm wondering if, as Bitcoins become more widely distributed, whether a transition from a proof of work-based system to a proof of stake one might happen. What I mean by proof of stake is that instead of your quote-unquote vote on the accepted transaction history being weighted by the share of computing resources you bring to the network, it's weighted by the number of Bitcoins you can prove you own using your private keys.
It went on.
If the implementation could be done, it proved to maintain at least a similar level of privacy and trustworthiness, and it's only minimally complicated the UX. And I'm thinking that a proof of stake-based fork could outcompete a proof of work one due to much lower transaction fees, since its network wouldn't need to support the cost of the miner's computing resources.
The blog post only ran 5 short paragraphs long, but proof of stake is now being looked at by some as a solution to trustless consensus without unreasonable energy costs. The essential innovation of proof of stake is that it does away with the competition between miners in a proof of work paradigm. Isn't it odd, frankly, that huge groups of Bitcoin miners have to compete in order to do something so simple as validate a transaction? It's necessary to prevent one dishonest node from pushing any fraudulent transactions, but a quite inefficient solution to that end. Under proof of stake, you'll still have miners, here called validators, but only one per transaction. Miners are chosen by chance through the blockchain's algorithm in proportion to the amount of stake that they have in the currency overall. So let's say we have a cryptocurrency operating under proof of stake. A validator with $50 invested in the system will only be able to mine 1/10 of whatever another validator with $500 could. Like proof of work, proof of stake has its own sets of advantages and disadvantages.
So I think proof of stake is a more kind of complicated paradigm. It's not really proven in any actual functioning system.
Where proof of work might incentivize mining pools that end up centralizing a blockchain, under proof of stake, there is no such incentive. In fact, because it doesn't require validators to have such powerful computers at their disposal, proof of stake environments encourage more participants in the validation process, therefore leading to further decentralization. Proof of stake also has its own organic means for keeping validators honest, since nodes lose stake anytime they approve invalid transactions. Plus, as a side note, a 51% attack like the one I described earlier would just make no sense under proof of stake. Anyone with over 50% of the network's mining power would also own over 50% of the network's monetary value by definition. If you really were that rich and still wanted to scam people out of their shares, you'd be contributing to the devaluation of the currency you're already so deeply invested in. At the same time, proof of stake is a bit less socialist, for lack of a better word, than proof of work is, since it rewards money with power. Because a $500 investor can process 10 times more transactions than a $50 investor can under proof of stake, they will also be increasing their earnings at 10 times the rate of their poorer counterpart, leading to its own kind of centralization. Ultimately, though, the number one concern you might have with proof of stake is that it's mostly untested in practice. Bitcoin demonstrated proof of work in a real-world environment. Proof of stake, to this date, doesn't have its own Bitcoin equivalent.
Today, proof of work is the solution that we have, and we know and that it works. There are various experiments and proposals for proof of stake systems. Some of them have known errors and known bugs. Others are promising, but the jury's still out in how these will fare in practice.
So here we have two remarkable, elegant, problematic solutions to trustless consensus in decentralized systems. Both are great, neither is perfect. Today's blockchain developers are often looking past proof of work and proof of stake to newer, perhaps less imperfect models.
In proof of work, the thing that you're using is your computing power. There are other systems that have proposed using other resources, such as proof of replication, proving that you store something, but proving that you store something many copies of it. Or proof of space-time is similarly, you're devoting a certain amount of resources over time. That's just two examples that come to mind.
When we were designing Helix, we followed a few guiding lines. So, first of all, we didn't want to invent a completely new consensus model. We wanted to use tested and proven building blocks out of older consensus protocols that were proposed. We decided not to use proof of work paradigm, which has, improved itself quite effective and secure. And the reason why we chose this is because we see also a lot of problems with proof of work, especially in our use case. So I think we're pretty close to a lot of the proof of stake suggestions that are being developed right now. It's just a question how you weigh the nodes. In proof of stake systems, you weigh the nodes by their stake in the system or by the amount of coins that they have. And we're doing something that's a bit different. We're looking at a reputation measure. We believe we can make the reputation measure be more relevant or more efficient, more effective than stake. Although in many ways we think that stake is going to be part of the reputation.
The problem of consensus in decentralized infrastructure is not one that will be solved in a single go. It'll require years of evolution with input and tinkering from some of the smartest minds in the industry. With today's models, we're already well on our way. Thanks for listening to this episode of the Orbs podcast. If you have a brilliant idea for a perfect consensus model, don't write me at nate@podeal.net. Get in contact with somebody much richer and more influential. If you don't have a revolutionary solution, but are still interested in continuing this discussion, email me and leave us a review on iTunes. I'm Nate Nelson. Until next time.
Blockchain. Produced by PI Media.